So if we have those numbers, what do we do with them? Well, that depends on how we want to recover from those packet losses. So we have two options. Two options for lost packets. Those two options are firstly, so these packets get to the home agent, they attempt to travel to the other end and are simply dropped. So what we can do is we can retransmit them from the source. So in other words, there's an end-to-end connection from the corresponding node all the way to the mobile node. These packets should be acknowledged. We'll talk about transport protocols next time. If there's no end-to-end acknowledgement of packets, the corresponding node will simply retransmit them. Question.
Why is the dead time not with respect to CN?
In fact, it's identical because, okay, so while this is the dead time with respect to the home agent, what is the dead time with respect to the CN? Well,
it'll be a bit extra. It'll be.
So, I mean, if a packet that's released here from the CN arrives here at the home agent, this packet can get through. Anything slightly later will not. This packet released by the CN here. Now, okay, this assumes that the connection is a stream and that there's no request from this end. So in that case, the corresponding node will simply continue sending packets. So the first packet that could possibly get through is the one that arrives right here. And that was released by the CN right here. So this is the dead time from the CN, and since these offsets are the same, it's the same time. Okay, retransmit from source, all lost packets. Are not acknowledged. And are retransmitted from the CN. Second retransmission strategy is that the home agent will buffer. So buffer at the home agent. In other words, the home agent will always remember a certain number of packets that were previously transmitted, and all the packets that were lost will just get retransmitted.
So just like in the context of the TCP connection.
Yes. So I mean, that is the basis of the retransmission. So TCP will acknowledge each packet. If the acknowledgements are not received, then the corresponding node will know to retransmit that. Question back here.
So in that case, in terms of the mobile IP layer, it doesn't have to do anything. I mean, if it's using TCP, then basically by definition it'll want to try again and make sure those packets get sent.
That's correct. Yeah. We will talk about. So this is looking ahead a little bit. I wanted to do this analysis just to emphasize the consequences of these switchovers, of these handovers, and so the only issue we need to think about with respect to the transport layer is the end-to-end packet acknowledgement. So we'll actually there are a lot of issues with mobile TCP compared to TCP and wired networks, and we'll deal with those next week. But for now, the only thing we have to worry about is acknowledgement. Okay, buffer at the home agent. The home agent keeps several previous packets and retransmits as necessary. question then becomes, fundamentally, it's the same number of packets as I argued over here. It's the same dead time with respect to the home agent as it is with respect to the corresponding node. So the question is just how many packets need to be retransmitted. It's actually the same answer in both cases. From the perspective of the home agent, the question would be how big does the buffer need to be?
Okay, like I want to optimize this because I want to do something clever.
Yeah.
I've got a mobile. I know that there are only so many adjacent foreign agents. So when I transmit to all the foreign agents. It comes into range, I do that. The foreign agent just updates you. You're always sending to a pool of foreign agents every time. So in a way,
So yeah, that's actually called, there's a name for that, it's called soft handover, when you maintain links to more than one base station at the same time. We'll talk about that, yes.
But if you did that, wouldn't you have a lot of foreign agents getting a lot of traffic that you just see the
That's right, so it's wasteful of bandwidth, so usually speaking, so in the same way that when you wander around with your cell phone, you are usually within range of only one cell tower, but sometimes on the boundaries you're within range of two, so usually you would only have links to either one or two foreign nodes, and that would only happen just as you're leaving one network penetrated. But yeah, maintaining those links is what allows these connections to stay alive without all this dead time as you're switching over. Question vector.
So each one of these packets, each one of them is being acknowledged by the mobile node to the home agent?
Yes.
But so why don't we consider the time for the packet to get acknowledged back?
So we will talk about that when we talk about TCP, but there's what's called a congestion window. So these packets are being sent. Let's assume the congestion window is very long. The corresponding node does not need to hear each packet being acknowledged before it sends the next one. So
Not the first one, the home agent.
the home agent, either way, it works the same way either way. So this end-to-end connection. I mean, think how that would work. You send a packet, you have to wait for the acknowledgement before you send another packet. So that would be the bandwidth of that would be quite low because there would be a lot of wasted time while you're waiting for that acknowledgement to show up. So what happens is in TCP you have this thing called the congestion window, which is basically the number of packets you can send before you hear an acknowledgement. So if we assume that that's very large, then these packets will just keep getting released even though this has been changed over and none of these packets over here have been acknowledged.
Is that MTU?
MTU? I'm not sure. Actually, I'd have to look that up. I'm not sure.